Okay, so we're on page 7 of Unit 5. We're talking about astronomy, space, and soon to be gravity. Kepler, who we've been talking about, Johannes Kepler, Kepler used data collected without the aid of a telescope. And this was collected over a period of several centuries. So he was using data that had been collected already in addition to his own. He even communicated with Galileo, probably not through email. Galileo, who is given credit for inventing the telescope. With his spyglass, he saw new things, including thousands of new stars. He saw the surface of the moon, which was rough and uneven. He even calculated the height of a mountain on the moon. Pretty interesting stuff. And the way he did it, he used some shadows and law of similar triangles. He discovered 4 new planets. Actually, what he found were the 4 big moons of Jupiter. Which are now named Io, Europa, Ganymede, and Callisto. This discovery was a big breakthrough for the heliocentric or sun-centered theory. Because something had been found that did not orbit the Earth. Remember the geocentric model? They thought that everything orbited the Earth. Galileo even calculated the period and orbital radius of each of the 4 moons. He also saw sunspots. Noticing that patterns return periodically, he calculated the sun's rotational period as 27 days. Today's value actually differs. It has a range of 25 to 35 days. He saw the phases of Venus. More proof supporting the heliocentric theory. Galileo's discoveries with the telescope did not end the geocentric versus heliocentric argument, but it sped up the eventual acceptance of the heliocentric theory. The year that Galileo died, the man was born in England. Sir Isaac Newton. Born in 1642, died in 1727. During a long 18-month vacation from teaching due to a plague, Newton was busy. He was working from home. He invented calculus. He developed the laws of motion. Remember Newton's three laws? Unit 3. And 3, he investigated optics, including how telescopes work. All this during a pandemic. What have you done during your pandemic? We will concentrate on his efforts to explain why the motions of the Earth, Moon, stars, Sun, and planets occurred the way they had, the way they had been observed for centuries. Newton disagreed with the Greeks on one major idea. The Greeks thought the natural motion of an object was in a circle. Newton said that natural motion of an object is uniform motion in a straight line. In order to travel in a circle, an inward or centripetal force is needed. But what is the force that keeps the moon in orbit around the Earth? The answer to that question may seem obvious to us, but the physics books of Newton's day only spoke of gravity as being a pull which affected things near the Earth. It sure couldn't reach all the way to the moon. There's this idea that Newton discovered gravity. People knew that gravity was a thing. They were aware that if you drop something, it's going to hit the ground. Newton started investigating this mysterious force, which must come from the Earth and must be felt all the way out at the moon's position. Using the formulas for circular motion, and these should look familiar to you from the previous unit. Centripetal force is mass times the centripetal acceleration. Centripetal acceleration is the velocity squared over the radius. Velocity is 2 times pi times the radius over the period. Remember when we combined these 3 formulas, we came up with another formula. Centripetal force 4 pi squared times the radius times the mass divided by the square of the period. So Newton goes a step further, and I'll show you what he did. There's not a whole lot of deriving here, just you can see what I did though. Newton looks over here and he sees this t squared. Remember Kepler's law? T squared equals k times r cubed. So here's what happens. 4 pi squared radius times the mass. And instead of t squared, Newton puts in the constant times the cube of the radius, which requires a little bit of simplification. For instance, here's the radius, and so we can rewrite this as r squared. So what we have here is the centripetal force. Let's break this up into some pieces and you'll see how it works later. 4 pi squared times the mass over k. Now, if you take a look at this, 4 is a number that doesn't change. Pi is a constant. K is a constant. The mass of an object isn't going to change, and so all of these things make up a constant. And the only thing that changes is 1 over r squared. 1 over the square of the radius. This is a relationship that we've seen before in other places, and we will see in places again. This inward directive force varies inversely as the square of the radius of the orbit. The force equals a constant times 1 over the radius squared. This relationship is found in many parts of nature. It's called the inverse square relationship. The math of this relationship says, as the radius doubles, the force is 1/4 as strong. As the radius triples, the force is 1/9 as strong. If r, the radius, is cut in half, the force is 4 times as strong. Newton was still puzzled about the source of this moon orbiting force until one day, while sitting under the apple tree, the question he asked, how high does gravity reach? People knew that if they dropped their pencil, it would hit the ground. People knew that if an apple fell off of a tree, so here's a tree branch, here's an apple. So they know that an apple from this height could fall and hit the ground. But Newton looks up and he says, what about an apple on this branch? Can gravity reach that high? Or, let's imagine this is a really tall apple tree. What about this apple in this branch? Could gravity reach that high? How far does the gravity reach? Could it reach the moon? Newton's revolutionary idea was this. Could the same force which pulls an apple to the ground exert an inward force on the moon to keep it in orbit? So here's how he proved it. Calculate the centripetal force needed to keep the moon in orbit. So for this, we have to know the mass of the moon. I'm not sure how Newton knew the mass of the moon. The mass of the moon, 7.2 times 10 to the 22nd kilograms. The period of the moon's orbit, 27.32 days. And we're talking about centripetal force, so we're talking about kilograms, which we have, meters and seconds. So we need to change days into a better physics unit, which is seconds. So 1 day is 24 hours, 1 hour, 3,600 seconds. 2,360,448 seconds. The Earth to Moon distance, which we need to make sure we're measuring this correctly. So here's the Earth, and here's the Moon. We are going to measure it from the center of the Earth to the center of the Moon. Center to center, not edge to edge, it's going to be center to center. And so this Earth-Moon distance is 384 times 10 to the 6th meters. In case you're wondering where this number came from, I'm looking at the sheet with the solar system data. The Moon, the average distance from the Earth is 0.3844 times 10 to the 6 kilometers, and so we can change that to meters. That's where that number comes from. So, to calculate the centripetal force, using the formula that we looked at, 4 times pi times the radius of the circle, which is the Earth-Moon distance, 384 times 10 to the 6th meters, times the mass of the Moon, 7.2 times 10 to the 22nd kilograms, divided by the square of the period. And in case you got lost there, that's the formula that we use. So when you type this in, you come up with 1.96 times 10 to the 20th newtons. This is the centripetal force required to keep the keep the Moon in orbit around the Earth. Part 2, calculate the strength of Earth's gravity at a distance equal to the Earth-Moon distance. So find the amount of force the Earth is exerting on the Moon, or rather find the Moon's weight. So at Earth's surface, gravity is 9.8 meters per second squared, which we usually just call 10. And so here's the relationship we're looking at. Force equals K times 1 over the square of the radius. From the top of the page, this is the inverse square of the radius as far as the gravity is concerned. Instead of K, so we're looking for the weight. Instead of K, we're going to use G. Times 1 over r squared. So at the Earth's surface, and this is really, if you were using this formula, 9.8 times 1 over 1 squared, because at the surface you are 1 radius away from the Earth. So at a distance of 2 Earth radii, we have 1 over 2 squared times 9.8 meters per second squared. Let's call this 1/2 squared times 9.8. Which means that we have 1/4 of the gravity of the surface. At a distance of 3 Earth radii, we have 1 over 3 squared, or 1/9 times the gravity at the surface. At a distance of 60 Earth radii, which is the Earth-Moon distance, gravity equals 1 over 60 squared times 9.8 meters per second squared. And this is really 9.8 over 3,600, 2.72 times 10 to the negative third meters per second squared. This is g, this is the acceleration. So to find the force, required, mass of the moon times the acceleration of gravity at that point, 60 Earth radii away, 2.72 times 10 to the minus third meters per second squared. And we come out to 1.96 times 10 to the 20th newtons. Take a look at this. Therefore, the inward force needed to keep the moon in orbit comes from Earth's gravity.